I'm David Swenson, and this is an OpenPath Sampling mini tutorial. In today's mini tutorial, I'm going to tell you about SimStore, our new subsystem for storage, and about the OpenPath Sampling Command Line Interface. All of this information is available online in our mini tutorials repository in the directory SimStore and CLI. This is the first part of a three-part series, and this one is going to focus specifically on getting your simulation set up using SimStore. So whenever you're doing any kind of simulation, there's sort of three stages. You need to set up the simulation, you run the simulation, and then you analyze the results of your simulation. And we're going to recommend that you do that in a very literal way here. So we're going to have three stages with two files in between. What we're going to do first is we'll use an IPython notebook to set up your simulations. And we'll create with that a file called setup.db. That .db suffix is because we're using our SimStore system now. If you were using netcdf plus, that would still be a .nc, and that would work fine. Once you have your setup file, you use that as an input to your command line interface commands, which actually run the simulation. This gives you an easy way to run the simulation on a cluster or something like that. The output of that then you will analyze, and typically you do that again in a Jupyter notebook. This is a little bit different from an older approach that we see a lot of people using, and is kind of suggested by some of our earlier documentation, which is to combine this setup and run process into one single script, one Python script that you run. We don't really recommend that, and the reason we don't is that every time you run something like that, if you create a new object, every time you create a new state definition, OPS has no way of knowing that the state definition you created is identical to the one you created before. If, on the other hand, you do the approach we're suggesting, where you do this setup.db as kind of an intermediate stage, that gives OPS a way of reusing the same object. You create it once and reuse it over and over again. So you can reuse those objects in the sense that if you're running one TPS simulation, but you really want to run multiple copies of it at the same time, you can reuse everything from your setup.db, and it will make your analysis easier. If you are running, possibly you're doing different kinds of simulations. First you're doing a TPS simulation, then you're doing a committer. If you reuse the setup.db for the definitions of your states, you're guaranteed that you have exactly identical state definitions. Today we're going to be focused on this first stage, which is setting up the simulation. It's the first phase of this CLI workflow, although we're not going to actually use the CLI today. It's just going to be about SimStore and how you can save to SimStore. It's important to emphasize again that the CLI and SimStore, these are two new ideas, relatively new additions to OPS, but they are independent of each other. You can use the CLI without using SimStore, and you can use SimStore without using the CLI. But they're very useful, especially in this context of the kind of workflows that I'll be showing in these tutorials. For this tutorial, we're going to study a really simple toy model of a dimer that can be in a sort of condensed form or an extended form. That dimer is in a bath of other particles, repulsive particles, WCA particles to be exact. This is a nice little model that's been used in a lot of methodology development and things like that, including the first TIS paper. In fact, we're going to do this with TIS. You can see on this I've marked where the interfaces will be. We'll do three interfaces. The nice thing with this model is you can change things like the barrier height, which is that H, or the distance between the states, which is determined by that W. This is, we're going to do this with a barrier height of 6 KT, which isn't too rare, but it's enough to make it an interesting problem. We're going to do this with OpenMM. You might have expected that we would do this with our internal toy models, but instead we're going to use one of the tools that's built into OpenMM Tools, which is one of the test systems that it comes with, which are designed to be easy to set up, commonly used test systems that are used in molecular dynamics simulations. We're going to be saving our files using the new storage subsystem, SimStore. These files end in .db, unlike our old storage, netcdf+, which ended in .nc. The advantages of SimStore, first off, it tends to be faster. It's smaller, especially if you're dealing with very small files. Like the setup.db file should be very small, and you'll see a huge difference between the size it is with SimStore and with netcdf+. Also, SimStore is designed for parallel simulations. As we move on to replica exchange TIS with parallel simulations, you'll want to be using SimStore. It's the only thing that will work. The disadvantages are it's not the default, so it does require some small changes to your scripts. I'll show you how to do that today. They're very small changes. There may be a few edge cases or things that it doesn't quite do the way we would like them to yet. It hasn't been in use for as long as netcdf+, and so it's still developing. It should be pretty solid and ready for production work, but if you come across any problems or anything where it just isn't as easy to use as you might like it to be, let us know. We're trying to get this to be fully ready for the 2.0 release of OpenPath Sampling. Here we have a Jupyter notebook. This is available to you in our mini tutorials repository under the SimStore and CLI directory. I will actually be running this using the slides mode. So the first thing we do, as always, is to do our imports. So we import OpenPath Sampling, we'll be using OpenMM tools, we'll be using SymTK units, NumPy, and mdtrash. Now the next thing we're going to do is the first thing that is different when you're working with SimStore. And so what we're going to do is we're going to tell OpenPath Sampling that we plan on using SimStore. First off, instead of using paths.storage, you'll have to get your storage from openpathsampling.experimental.storage. We'll also get out this monkey patch all, and you see we use that to monkey patch OpenPath Sampling to tell it, hey, we're going to use SimStore. We also need to do the same thing for collective variables. That is, we need to get collective variables out of the experimental storage sub-package. And finally, we do need to, when we're dealing with transition interface sampling, we need to inform the interface set that we are using SimStore. But that's all you really need to do. Now we're going to talk about setting up our TIS to work on that double well dimer system we talked about. So the first thing we want to do is, even though OpenMM uses explicit units, we kind of want to fake like we're using dimensionless units. And the first step of that is going to be that the real Boltzmann constant is Boltzmann's constant times Avogadro's constant, because OpenMM reports energies in units of energy per mole. Once we've got that, we can define our mass, our energy unit, epsilon, and our distance unit, sigma. And we define these based on the Leonard-Jones or WCA parameters for argon. So that's just a basic, easy definition. By having defined those, we have also automatically defined a unit of time, which we will call tau. And then when we are working with mdtrash expects things to be in units of nanometers. And we have here things that we're going to be thinking in units of sigma. So we need to keep around this sigma in units of nanometers in order to convert for mdtrash. We will use this temperature, and then these double well parameters are from the original TIS paper, and that includes a barrier height of 6 kT. Not terribly rare, but good enough. So now we're going to work on setting up our engine. The first thing we have to do is set up the OpenMM side of that. So we'll use the OpenMM tools.testsystems double well dimer in a WCA fluid test system. We tell it we're going to have one dimer in 216 particles total, density 0.96, and then all of these other parameters are just what we defined them as previously. We'll use the VVVR integrator. Note that our time step and collision rate are defined in terms of tau, our unit of time, and then we'll use that energy, or that temperature. We'll use that temperature that we talked about earlier. From there, we just wrap the OpenMM stuff in the OPS object. So we start with the topology. The test system knows its mdtrash topology, and so we wrap that in an OPS mdtrash topology wrapper. And then for the test system knows its OpenMM system object, testsystem.system, which is needed for setting up the OPS OpenMM engine. And we set the standard engine options in addition to that. We're going to want an initial snapshot that we can then use later on. And to do that, this is mostly OpenMM under the hood. So the OPS engine created an OpenMM simulation object. And then that simulation object can have its position set to what the test system had as its initial positions. And from there, we can minimize the energy using OpenMM to do that. And then we extract the current snapshot as an OPS snapshot from the engine by asking for its current snapshot. And that just takes a couple moments. Next stage in setting up your path sampling simulation, you've got your engine. So now we're going to set up our CVs and define our stable states and our interfaces. So here again with CVs, there's a slight difference between the new way of doing it and the old way of doing it. The old way of doing it, you would do paths.mdtrash function CV, and then the first thing you give it has to be a name. All CVs had to carry names. That's no longer true in the new storage. However, you can name a CV just like you would name any other object in OPS with the .named function. Other than that, it's the same. You have the function that you're wrapping, md.computeDistances. For mdtrash functions, you need to provide a topology, and then any additional keyword arguments that go to that md.computeDistances. In this case, it is atom pairs, and we're looking at the distance between atoms 0 and 1. We can define our stable states. Again, it's pretty much the same story. So our condensed state is anything less than a distance of 1.2 between those two particles in the dimer. The extended state is anything greater than 1.54 sigma. And so because the CV is going to report in terms of nanometers, because it's coming from OpenMM, we need to define our lambda min and lambda max in terms of sigma nm, multiplied by sigma nm. Technically, I guess I should do the same for the infinities, but of course it doesn't really matter when you're talking about infinity. For the TIS interfaces, we will use the volume interface set and again define our interface values at 1.2, 1.26, 1.32 times sigma nm. I used a NumPy array there just so I could simply multiply once by sigma nm, otherwise I'd type 1.2 times sigma nm, 1.26 times sigma nm, etc. It's just a little bit easier with NumPy. With all that created, we're going to actually create the network, the TIS network in the move scheme. We're going to study the process of going from the condensed state to the extended state through our interfaces that we defined. And so we'll use an MIS-TIS network for that with only one transition in it. And we'll do the default replica exchange scheme for transition interface sampling that comes with OpenPath sampling. Now we save everything. Again, there's a little bit of a change here. It actually is to make it easier for you. So in the old storage, you needed to save, if you had any collective variables, you needed to save a snapshot as a template. If you're doing transition interface sampling, you also need to save a trajectory as a template. With the new storage, you don't need these templates anymore. So now what we do is we open the storage for writing using storage setup.db. We're a DB file now. We save the snapshot, not because we need a template, but because we're going to use that as our first snapshot, our initial conditions, when we run dynamics. In the next session, we're going to go from running snapshots all the way to running transition interface sampling, just starting from that snapshot that you give us. And so here we save it, and we save also the scheme. Then we can also save other information. This is an important thing that was already available in NetCDF+. We could tag nearly arbitrary objects. And so tau, which is an object carrying a SimTK unit, can be saved. We can use that later so that we can calculate our rates. Our rates will be reported in terms of per picosecond, but if we want to report them in per tau, we need to know what tau was. And similarly, we're going to save sigma nm because we'll be looking in the analysis at some of the output from the CV that we calculated, and we'll want to be able to turn that into something we think about in terms of sigma instead of in terms of nanometers. Do that and close the storage. We're going to want to get this initial trajectory that we'll do using a high temperature molecular dynamics engine. And so we need to set that up as well. It's easy enough. All we're going to do is take the same kind of integrator we did before, but we'll run it at twice the temperature that we had previously set up. And then we'll create an engine that is appropriate to that. Once we've created it, we will reopen our storage in append mode and save our engine and close it storage again. And with that, we're ready to start actually running things on the command line using OpenPath Sampling. I hope you'll join us for the next session where we will start with the snapshot that we stored and go all the way to running transition interface sampling simulations without doing any Python at all. It'll all be done just with the OpenPath Sampling Command Line Interface.